In this video, I'm going to talk about what is nonlinear modeling and how we can build a nonlinear model using R. So the outline for this particular session is that we'll start with an example, and then we'll try to understand how we can use nonlinear modeling in this particular example, and then we'll talk about the R application. That means how do we build such a model in R, and then I'll talk about the different functional forms involved, or different functional forms available in nonlinear modeling, and when is and when do we use what form. Okay, so here this background is this example. Okay, there's a marketing manager who would like to forecast the year-end performance of a given product. So it's in the market and it's selling in the market, and the company or the marketing manager is trying to understand, or trying to forecast rather, so what is going to be the year-end performance of the particular product. Okay, so the data that's available with us is like this. We have the weekly data, and we have number of household who have purchased the product, the given product, and it's increasing with week, right? It started with 8, 14, 16, and so on. So we'll try to focus in percentage term. Okay, so here is the better data. We have house weeks, and we have the corresponding number of household who have purchased the particular product, and then we have the proportion of household that has purchased the product. Okay, and this is how the data looks like. Okay, the data is nonlinear. As you can see, the pattern of the data is nonlinear, right, with respect to the number of weeks. Okay, there's no linear pattern, it's clear, right? So this is a typical data in which we should ideally be using a nonlinear model instead of a linear model. We'll talk the difference between these two types of model, what the options are, and then how do we choose what option is the best for this given data. So if you have such a data, the first option that comes to your mind is using a linear regression. So the ordinary least square regression is one commonly used options in regression analysis. But given the fact that this particular data is nowhere linear, or it is not something that would suit a linear regression line, then we'll just opt out of it. We'll not go ahead with linear regression. Polynomial regression is an ideal thing to do here. Okay, instead of just taking, let's say, the linear regression is like a equal to beta naught plus beta 1 x, where x is the independent variable, y is the dependent variable. Polynomial regression, on the other hand, you just add a couple of more terms of x. So the polynomial regression could be something like this: x plus beta 2 x square. So it takes care of some form of nonlinearity in the data. Okay, but what exactly should be the number of x terms, like whether you should have just the quadratic x, or you could also have a cubic x, you could have x cube as well, or x to the power 4, x to the power 5. So how many number of such terms are going to be there is of course a challenge, and then you find it out what is the number of suitable x terms that should be there in the model. The third option that we have is use a nonlinear form of regression model, which is taken from the literature. So in the research literature, whether it's marketing science, whether it's any natural science, biology, or botany, or any engineering research, so there are a number of predefined models, theoretical models, which are often used. The theoretical models will of course have parameters which have to be then estimated from the data, but there is always a functional form given to you. You do not have to find it out from the data, it is given theoretically. Okay, and then it will more of a backward approach. Normally what you do is that you have a data, and then we find out what the functional form is. Okay, but it is exactly the opposite. We have functional form from the literature in nonlinear regression form, and then we fit it to the data. Okay, so it's exactly the opposite. One thing to remember here is that nonlinear regression is something that we define when the regression is nonlinear in parameters, not in variables. For example, this is not a nonlinear regression; it's still a linear regression, some form of linear regression. Okay, so polynomial regression is a special case type of linear regression. Okay, um, whereas if you have a model like this, y equal to a naught x1 to the power beta 1 x2 to the power beta 2. Okay, so the relationship between your y with respect to this betas is something that is not linear. It's nonlinear, right? So the relationship should be nonlinear in parameters, not nonlinear in variables. Here it is nonlinear in variable. Y is nonlinear with x, but betas are all still linear, right? But here in this particular equation, you can see that the betas are related to y, the dependent or the target, um, nonlinearly. That's why this is a typical example of nonlinear regression equation. Okay, so for this particular type of data, so we already have a theoretical functional form y equal to p naught 1 minus e to the power minus bx. So y is the target. So here we have proportion of household, and x is the number of weeks. Okay, so that's what we'll use as one of the independent variable. And we have two parameters to be estimated: p naught and b. Okay, and p naught in the literature it's been defined as saturation proportion. Okay, and then beta, sorry, b is known as decreasing returns parameters. Decreasing returns parameters. Okay. Now we will not get into the details of what the definition of these parameters are, but we can, intuitively understand what these parameters are. So when x equal to 0, so when x is equal to 0, your basically y is 0, right? Y is 0. Because your p0 is multiplied to 1 minus, when x is equal to 0, e to the power 0 is again 1. So 1 minus 1 is 0. 0 multiplied to p0 is 0, which is y equal to 0. So it passes through. So the regression curve will passes. So instead of a line, will have a curve here, right? It will passes through the origin um, or the starting point in the xy plane. All right, having this in mind, so what we will do here is that, so this particular functional form is nonlinear in nature. Okay, if you see the b is related to y in nonlinear, right? When y is a function of e to the power b, some form of e to the power b, so y is related to b in nonlinear way. Okay, and that's exactly the reason why we call this as a nonlinear regression equation. Okay, and all you need to do is that you optimize this, optimize the values of p naught and b, so that the curve will fit the data to the best possible extent. Okay, so unlike your other regression equations where you do not quite provide the functional form to the estimation process, here we'll have to provide that. Okay, and I will show you how we can do that in R, where we actually explicitly provide the functional form. So estimation. So how do we estimate? OLS is used, least square estimation is used in linear regression equations. Here, the estimation process is somewhat different. Okay, so nonlinear least square is used instead of linear least square, and weighted nonlinear least square is also used. And there are various forms of this, estimation process. There are many algorithms. In least square regression algorithms, you have also many algorithms such as Newton-Raphson, quasi-Newton, and so on. Here you have the four main important or four most popular algorithms used. One is the steepest descent or the gradient method. The second one is the Newton method. Third one is the modified Gauss-Newton method, and the fourth one is the Marquardt method. Okay, so most of the times, you will have the software, taking the default or the best out of these four. But if you really want to, you're curious about knowing how the estimation process is going to be different with the different types of optimization algorithm, you can try it out. You can define this one and see the result, and then define, then use this next one and compare the result across these algorithms to see which one actually gives you the best result. But most functions in softwares will provide the optimal result out of this four. All right. Now, in the estimation process, as we all know, we not just want the parameters, p0 and b. We also want the confidence intervals for these parameters, right? In linear regression, you might have heard about what confidence intervals are. So how do we get those parameters? Well, those parameters can be found out by bootstrapping. Okay, so you can bootstrap yourself, or if the software itself has its as an internal feature, then it will provide that to you directly. So bootstrapping is nothing but resampling, where you find out multiple samples, fit the equations, and find out the values of p naught and b. Okay, and then find out the standard deviation. Okay, that's what is nothing. That's what is going to give you the parameters. Sorry, the confidence interval. So in one case you will have p naught plus your standard deviation. The other case will be p naught minus standard deviation. So it will, so the p naught will lie between this two extreme points. Okay, it's as simple as that. So there is a video on my channel on bootstrapping, where I have just explained how you can use bootstrapping to find out confidence interval in cases where you do not get confidence interval by default. In most nonlinear regression equations, you will not get the confidence intervals directly from the software. Okay, if you're lucky, you might get, in some software do have these features, but most of them don't have. So you need to, in case you need that, you will have to do it yourself. So just take 100 samples from the same sample, just do it with replacement, and fit this equations, the functional form that we just talked about a couple of slides ago, and you will have 100 radials, right? 100 beta, sorry, 100 p0 and 100 b. Find out the standard deviation of these 100 p's and 100 b's. Okay, and then that will give you the confidence interval, right? Once you have the standard deviation in place. What about the significance test? Well, there is no normality assumption, much like your linear regression. So you will not need to confirm that the error term in this case is significant. Error term in this case is normally distributed. That the requirement is only there in linear regressions, and hence you need not get a significant significance level of p naught and b. If you try to explain the significance level, that won't make sense, because the assumption of normality is very strict when it comes to explaining the significance level. So t-test is something that cannot be done in this case. Of course, there are other tests, statistical tests, that can be used to find out some kind of significance, but that is up to you if you really want to know. The interesting thing about using nonlinear regression is that you use nonlinear regression when you are mostly interested in prediction rather than explaining the relationship. Okay, and when you're doing prediction, significance test takes a backseat. It's not that important. Okay, so when your intention is to predict for future values, then significance test is something that you can ignore for the moment. How do you finalize the best model out of several models that you will be fitting? So you just find out the root mean square error. R square is something that's often not used. In such case, you can of course find out the R square, but R square is mostly used in linear regression. So root mean square error instead can be used. Just compare the one that gives the least root mean square error is the one which should ideally be selected, or is the best model or the most optimal one. Here is the data. So we have fit the model, and I'll show you the code later on, but just to show you the result, we have the week and the household proportion, and this is what the predicted value is. So this is the actual value that we had, and when we fit the model with the functional form that we discussed, we just found it out. Okay, and then we find out the difference. When you take the mean of this, okay, mean of this difference of actual minus the predicted, and of course the modulus of that, you will get the mean square error. Okay, and then root mean square error is just the summation of that divided by the n. So the parameters are the following: p naught, which is 0.08, and beta or b, which is 0.064. Okay, now once we have these parameters in place, we can extrapolate that to future. Okay, with increase in the week, we can just extrapolate that to future weeks. So here is the graphical plot. Okay, you can see this is our predicted value, and the actual value is the dark blue line. Okay, there are areas where it is doing well, like here it is doing well, here also it is okay, but there are areas where there is some significant difference. Okay, even here, right? So there are a few places where it is not fitting your data very well, but the form of the regression equation is such that it is trying to generalize. So instead of fitting a line, it is actually fitting a curve, which is generalizing in a better way than a regression line. You can also find out the threshold where it is saturating. You can see that it is going up very steadily, and there is one point of time when it is saturating. There is no upward trend, rather it is somewhat parallel to the x-axis, so it's saturating. It is the increase is less significant. It's more of a straight line, right? So using this particular functional form, you can find this particular point where it is saturating. So there are many ways you can find it out. You can just visualize and have a threshold. That's the most the crude way of doing it. You can also use some optimal techniques. So just use an optimization technique to find out where exactly it is the slope is the least change in the slope. Okay, just find it out in different section of this curve, and it's easy in that way. All right, so how do we do this in R? Okay, in R we just use the function NLS. Okay, so takes care of the nonlinear regression equations. We have this target variable, we define that, and then we define the functional form. I was telling this that in nonlinear regression you will need to provide the functional forms, unlike in linear regression equation, when providing the functional form is not a mandatory thing. And then you'll also need to provide the starting values. Okay, and starting values sometimes play some big role. So we'll have to provide the starting values of p naught. This will be used for optimization, and if you're familiar with any of these nonlinear optimizations, you will know that optimizations happens iteratively, and if you do not provide the starting values, the initial values, then it will take the initial values as default values, and then that might take more time. Sometimes you could end up at local minima and so on. So if there is some information in the literature as to what exactly should be the starting values or the initial values, take that as the starting values. Okay, if you don't have, then the default values are also okay. Okay, so when you run this, you will get the the p values and the beta and so on. Okay, you get some form of significance level. Okay, so you are lucky if you are getting that, but it's not there in many other softwares, by the way. Okay, you're also getting the residual standard error. You're also getting what else? The confidence interval is not there, so you don't get confidence interval here. So you need to get it yourself if you need that. Okay, the second part of this particular session, I'll just spend some time in understanding what are the different types of nonlinearity that you will come across, and different types of forms of nonlinearity, and the motivation behind this, nonlinear models that appear in the literature. Okay, so first model that I'll talk about, which is well known to you, is that a simple linear model, which is a straight line model. Okay, we are interested in two things, an intercept and the slope, right? If y equal to a plus bx is the regression line, we're interested in a and b, and using a and b we can forecast future. We can also try to understand what is the change in y when x changes. Okay, so we can take a derivative of this, and we can find out the change in y when x changes to some extent. Okay, that's one way of building a regression model that finds a relationship and also does the prediction. But linearity is not always the case. There are situations where you have more complications with the data. There will be nonlinearity, there will be nonlinearity with saturation, without saturations, and so on. We'll see a few of these examples. So here is this case where linear regression line will not fit. You cannot fit a straight line with just y equal to a plus bx type equations. That's not possible. The second case is where it's not only nonlinear, it is also having a saturation. That means it increases, but at one point of time it doesn't increase anymore. The increase in the value of y is stabilizing, or it is very flat. Okay, so you need a different type of functional form for such type of data. Few more examples. Here it is a convex one. It is increasing and increasing rate. So increase in increasing rate will be somewhat convex. Okay, so this is like increase in decreasing rate, and then increasing rate, then saturating, and so on. Some sort of kind of S-sept. This is S-sept curve. Okay, third one is increasing at decreasing rate. Okay, so here also you have some threshold. Here you won't have a threshold because it is increasing. Okay, it's very unlikely there will be a threshold for y. Okay, but here there can be a threshold for y, because after that there is no increase. Here it is totally different. It increases, saturates, and then it decreases. So the motivation behind using different types of non-functional forms is because the way the data behaves is different. Okay, so accordingly you will have to choose the best form of functional forms, and in many literature you will find this has been experimented by other researchers, and you already have some kind of functional form to the data or the research questions that you're working on. Few more. So just the functional form we will see, and we have seen the graphs. We'll just see the functional forms. The first one is the linear regression line y equal to a plus bx. I've talked about in detail. It's simple. There's no saturations. There's no threshold here. Okay, there's no saturation and no threshold. Okay, and it passes to the origin. Sometimes you will have equations where this doesn't passes to origin. This will pass the origin when a equal to 0, right? When there is no intercept. So the second one is the fractional root model. Okay, so here it is like y equal to a plus b x to the power c. So this is a typical nonlinear model. Okay, this is not linear because the relationship between y and c is not linear. With a and b it's linear, but with a and b it's linear, yes, but with c it's not. So it's a nonlinear model, and c can be interpreted as elasticity when a equal to 0. So this is a case where it's linear, it's increasing or decreasing depending on the value of c. Okay, if that is the case, then you will try this type of functional form. This is called exponential model. Okay, so exponential regression model is also one form of regression model. This is also a typical form of a nonlinear regression model, because the parameter b is nonlinear related to y. Okay, so this could be increasing or decreasing depending on the value of b. This is Adbert functions. This is again nonlinear. C and D both are nonlinear related to Y. So this is a typical form of nonlinear regression model. It accepts accept and concave, and it has also saturation effect. Yes. The next one is the multiple instruments model. This is some kind of additive model for handling marketing instruments. So this is a typical marketing model where it's still some form of a linear regression model because the parameters A and B are A and B, yes, are related to Y in linear form, not in nonlinear form. So this is still a linear regression model, but with some kind of a different functional form. Okay, so this is multiplicative model, but again used for marketing. Okay, where x1 and x2 are two different parameters, so two different variables, and B and C are the parameters. B and C both are related to Y nonlinearly, and these are known as the elasticities. Elasticity is nothing but how it affects your dependent variable when x changes to some extent. Okay, so that's why elasticity is defined. Okay, you can read more about it, how you can find elasticity in the particular equations. It's just the rate of change of one thing with respect to rate of change of something else. It's widely used in marketing. Okay, yeah, a few points to keep in mind while you are building a nonlinear regression model. Nonlinear regression models are nonlinear in parameters, not in variables, and this is one confusion many people have. Many people think that a polynomial regression model is a nonlinear model, but that's not actually a nonlinear model. Okay, although loosely it is, but by definition, by statistical definition, it's not. Since the motivation is for prediction, not to understand the relationship, which of course is the secondary objective, cross validation is something that should be used. Okay, so you try out many types of functional forms and choose the one which gives the best value or the best performance in a cross validation. In cross validation, is just that taking out different test data sets and looking at the performance. Okay, so you start with the main data set, divided that into two types, training and testing. Build the model in the training and test it here. Okay, and try all functional forms. You are guessing those functions to be perfect for your model, perfect for your data, and then test that those models in the test data and see which one is giving the best result. So the comparison should be made across different types of models, not just a given functional form. No matter how specific the model or the functional form is from the literature, you can always try out different other functional form, which in fact will add more to the previous literature, and then people who will be doing the research later on can take some cue from your work. Okay, so it's always good to try out a number of functional forms and see which one works the performs the best in the test data set or in a set of test data sets. Okay, thank you.